In this video of capital budgeting, we'll look at an example of internal rate of return. Assume the following cash flows from two projects. So we have been given years up to 4 years, and then we have been given the cash flow for project S and project L. These are all in rupees. So initially the outflow or the investment into the project S as well as L is 1000 rupees each, and then subsequently there are cash inflows from both the projects. Assume that the cash flows are occurring at the end of each year. Find out the internal rate of return for these projects. The cost of capital is 10%. So project S is a short-term project which generates the cash inflows during the early stages of the project, whereas project L is a long-term project and it generates cash flows in the long term. Now let us first represent these two projects on a time scale. So these are the two time scale representations for project S and project L. Note that the cash outflows are represented with a negative sign. This negative sign is just to indicate that this is a cash outflow from your pocket, and the positive signs indicate that these other cash flows are cash inflows. That means they are coming into your pocket. So let us first take project S and find out the internal rate of return, or IRR. So what is IRR, or internal rate of return? Internal rate of return is defined as the discount rate using which the present value of all the cash outflows is equal to the present value of all the cash inflows. So present value of cash outflows is equal to the present value of cash inflows. Now, of course, when we say present value of cash outflows is equal to present value of cash inflows, we are just considering the absolute value of the cash inflow or outflow. We don't consider the negative sign here. Now, what this means is that IRR is the rate that forces the NPV to be equal to 0, because NPV is the net of all cash flows. So when we do the net of all cash flows, we'll represent cash outflows as negative and cash inflow as positive. But both the outflows and inflows are the same. So positive of an amount minus the same amount will become 0. So IRR is the rate at which NPV is equal to 0. So let's say the present value of the initial investment is represented as PV0. The present value of the first cash inflow is PV1. The present value of the second cash inflow is PV2. For third it is PV3, and the fourth it is PV4. Now what is NPV? So NPV will be equal to the sum of all the cash flows, outflows and inflows. So PV0 plus PV1 plus PV2 plus PV3 plus PV4. Now NPV has to be 0 at IRR. This is equal to, now PV 0. So for the cash outflows, we will take a negative sign. So PV 0 will be represented as minus 1000 plus PV 1 500 will be discounted at IRR to create PV 1. Now we know that PV is equal to the future value divided by 1 plus I to the power n. N is the number of compounding periods. I is the rate of interest per compounding period. This in our case is R. So PV1 is future value 1. So in this case, the future value is 500 and PV1 is the present value. So present value is equal to 500 divided by 1 plus R to the power n. Now 500 is being discounted for 1 year. So this becomes 500 divided by 1 plus R to the power 1 plus for PV2 400 divided by 1 plus R square plus 300 divided by 1 plus R cube plus 100 divided by 1 plus R to the power 4. Now this can be solved using the trial and error method. So in the trial and error method, the approach is to select any discount rate to compute the present value of cash inflows. Now then there will be two possibilities. One is that the value of this right hand side is greater than 0. In that case, we need to lower the value of the right hand side. And if we have to lower the value of the right hand side, we will have to increase the denominator. So that means we'll have to increase the rate of return. The other possibility is that the value of right hand side is lower than 0. In that case, we need to increase the value of right hand side. So if you have to increase the value, then we'll have to lower the denominator. So we'll have to lower the rate of return. So for this example, let us first consider R equals to 14%. Now let's calculate the value of the right hand side. So right hand side is equal to minus 1000 plus 500 divided by 1 plus 0.14 to the power 1 plus 400 divided by 1 plus 0.14 square plus 300 divided by 1 plus 0.14 cube plus 100 divided by 1 plus 0.14 to the power 4. So this is equal to minus 1000 plus 500 divided by 1.14 plus 400 divided by 1.14 square plus 300 divided by 1.14 cube plus 100 divided by 1.14 to the power 4. So on calculation, we get the values minus 1000 plus 438.6 plus 307.79 plus 202.49 plus 59.2, and this is equal to 8.08 rupees. So we had a negative sign of the cash outflow and the positive signs for the cash inflows. So the net right hand side value is 8.08 rupees, which is greater than 0. The left hand side is 0, whereas the right hand side is 8.08. So what that means is we need to lower the right hand side. Now if you have to lower the right hand side, we have to increase the denominator. So if you have to increase the denominator, let's take the next number, which is 15%, and let's see what value we get with 15% as the rate of return. So just to understand the concept that I'm talking, where we have to lower or increase the denominator, let's say you have 10 divided by 2. So this is equal to 5. Now if we increase the denominator, we get 10 divided by 5, and here we get 2. So if the denominator increases, the value of the answer decreases. So here I have noted that at the rate of return of 14%, the net present value comes out to be 8.08 rupees. Now let's find out the net present value at R equals to 15%. So now in this equation, we have to replace R with 15%. So let's just consider the right hand side. So right hand side is equal to minus 1000 plus 500 divided by 1 plus 0.15 to the power 1 plus 400 divided by 1 plus 0.15 square plus 300 divided by 1 plus 0.15 cube plus 100 divided by 1 plus 0.15 to the power 4. So this becomes minus 1000 plus 500 divided by 1.15 plus 400 divided by 1.15 square plus 300 divided by 1.15 cube plus 100 divided by 1.15 to the power 4. Now this comes out to be minus 1000 plus 434.78 plus 302.46 plus 197.25 plus 57.175, and this total comes out to be minus 8.335 rupees. So at the rate of return of 14%, NPV is 8.08 rupees, while at the rate of return of 15%, the NPV comes out to be minus 8.335 rupees. So NPV will be 0 somewhere in between 14 and 15%. So let's find that out. So let's say this is a time scale. Here we have 0. On the right hand side, let's say we have 1, 2, 3 and so on. And let's say this is 8.08. This we are getting at 14%. And here similarly we'll have -1, -2, -3 and so on. So here we get -8.335. And this is coming at 15%. So the total gap here is 8.335 on the left hand side plus 8.08 on the right hand side. So 8.08 plus 8.335, and this comes out to be 16.415. So 16.415 is the total distance to be traveled from 14% to 15%, or from 8.08 to -8.335. Now out of the total 16.415, in order to reach this point of 0, because we want the NPV to be 0, we have to travel 8.335 towards the right hand side. So if the total is 16.415, then to be at 0 we have to move 8.335. So if the total is 1%, right, the difference between 14 and 15% is 1%. So if the difference is 1%, in order to get to 0, how much do we have to move? So cross multiplication, let's say this is x. So we get x into 16.415 is equal to 1 into 8.335, or x is equal to 8.335 divided by 16.415. Now this is equal to 0.507. So basically we have to reduce 0.507 from 15, because we are moving on this side towards 14. So 15 minus 0.507, this is equal to 14.493. So basically this is the rate of return at which NPV is going to be 0. So 14.493% is the IRR for project S. Similarly, if we do the same type of calculations for project L, we'll get the IRR equal to 11.8%. So now we have been given that the cost of capital equals to 10%. So basically this is the percent at which we have borrowed the capital from somebody else. And both the projects are going to give us more than the cost of capital. Hence, if both projects are independent of each other, then both the projects should be accepted. However, if they are mutually exclusive and only one of them can be accepted, then project S should be chosen as it is giving a higher internal rate of return. Now the same calculation can also be done using a financial calculator. So let's see how we can use a financial calculator to find out internal rate of return. Now the method to use the financial calculator to find out the IRR is similar to the way we use the financial calculator to find out the NPV, or the net present value. So let's consider the case of project S. So the cash flows C0 is minus 1000, C1 is 500, C2 is 400, C3 is 300, and C4 is 100. So let me pull my calculator. So we have to enter the value of the cash flows in the chronological order. Now CF0 is cash flow 0, or the C0 cash flow that we have represented here. CFJ represents all the remaining cash flows, so C1, C2, C3, C4, and so on. Now the method to use the financial calculator is that first we enter a number and then let the calculator know what that number stands for. So first we'll enter the value of CF0 or C0. So 1000. Now this is negative, so we'll change the sign. Now we have to make the calculator aware that this is the value of CF0. Now CF0 is written in blue, so we have to press the blue button here, G, to activate that button, and then we'll press CF0. Now next we'll enter 500. So 500, and this is the value of CFJ, where J is 1. So again we'll activate that and click on CFJ. Then 400 G and CFJ. Then 300 G and CFJ, then 100 G and then CFJ. So now we have entered all the cash flows, and now we have to find out the IRR. So you can see this IRR written here in front of this button. So this will get activated when I press this F button here. So now I can press on IRR. So IRR is 14.4888. So IRR for project S comes out to 14.48 or 49. And the value that we got through our calculations was 14.493. It was very close. So this is how you can find out IRR using the formula, method, and the financial calculator.